Hi, I am Mercader, Application Engineer of Tabor Electronics. I am going to show you today a demo on direct generation and acquisition of microwave radar signals using the Tabor Electronics Proteus arbitrary waveform transceiver. The Proteus line of products from Tabor Electronics consists in a series of monolithic instruments incorporating up to 12 channels, and also PXI modules incorporating up to 4 channels of generation and 2 channels of acquisition. Those PXI modules can be integrated into any PXI standard chassis, along with other instruments or devices from different suppliers. The basic characteristics of the Tabor family of products are listed here. Basically, it can reach up to 9 gigaamperes per second as a generator, an arbitrary waveform generator, and up to 5.4 gigaamperes per second as a digitizer. In both cases, we have larger than 8 gigahertz bandwidth for both generation and acquisition. The number of channels can be huge, up to 12 channels in a single monolithic device, as I said before, but in a PXI system, you can incorporate up to 40 channels per chassis for 19 inches PXI chassis. It has a very large memory, up to 16 gigaamperes of memory, and associated to this memory that can be segmented to have an extremely powerful sequencing capability in the device. Finally, it has a very advanced triggering system with the lowest available trigger jitter in the market, which is especially important for radar applications. This is the block diagram for the instrument. As you can see, there is an input section with up to 2 channels at 5.4 gigahertz sampling rate and 4 channels of generation up to 9 gigaamperes per second. Associated to that, you have a very large memory, 16 gigasamples, and an FPGA that can be used also for the implementation of custom applications such as signal processing chains for both signal generation and acquisition, or real-time, very fast closed-loop control, such as the ones that could be required for echo emulation in a radar system. Okay, today we're going to use one of the modules, the IWT modules that you can see in the right. The IWT modules incorporate both generation and acquisition channels. In the left, you can see the AWG only product, which incorporates only generators, generator channels. Okay, so we have one of those each here in this PXI chassis. But we are going to use the AWT module that you can see here. As you can see, we have models capable of generating at 1.25, 2.5 gigaamperes per second, and 9 gigaamperes per second, which is especially well designed for microwave signal generation and acquisition. As we are focused quite a lot in the RF microwave market, it's important to be able to produce and acquire those signals in the right way, and we incorporate both digital up converters for the signal generator and digital down converters for the acquisition digitizer. Here you can see the block diagram for the up converter in the generation section. You have one of these in each one of the channels, which can be controlled independently. As you can see, we have the capability of storing IQ samples in the waveform memory at a much lower sampling rate. We can then upsample those signals by using an interpolator, and then the output of those 2 interpolators, I and Q, is supplied to an IQ modulator, a numerical IQ modulator, so you can produce a complex modulated carrier, and then you can control the carrier frequency used by controlling the DDS oscillators, the numerical control oscillators that you see in this block diagram. So you can change from one frequency to another without having to download a new waveform. It can be done on the fly. For the same thing we have for the digitizer section. Digitizer section we can use two steps down conversion. In the first step we produce a down converted image at the first Nyquist band of the digitizer by using undersampling. And then, as you can see here, you can go from the fourth Nyquist band to the first Nyquist band by selecting the right sampling rate. And then, once we have reached the Nyquist band in the first Nyquist band, we can apply a second stage of down conversion based in a digital down converter that produces directly INQ samples, decimated INQ samples. So sampling rate of the output is also much slower than the acquisition sampling rate. So reducing the amount of information to be processed by the post-processing system. Okay, good. Today we are going to emulate this kind of situation where you are sending some, transmitting some radar signal, and then you are acquiring the echo, and you process the echo accordingly in order to extract the information about the target. Okay, in this case, we are showing a multiple antenna system with multiple independent generators that can be adjusted in delay and phase. You can produce at the same time multiple beams and multiple signals tracking different targets at the same time. In order to have a simple to follow demo, we are going to use only one channel, one transmitter channel, and one receiver channel in this demo. As I said before, the goal of this architecture is to provide users with a very good signal generation capabilities, including RF quality of the signals. At the same time, the same thing for the acquisition side, but doing that, providing a large number of channels, like here, where we have up to 40 channels of signal generation, up to 20 channels of signal acquisition in a single chassis, in a single 19-inch chassis, which is an amazing number of channels. And at the same time, we provide complete timing and carrier phase control. So we make sure that you have coherent, pulse-to-pulse coherent carriers, and you can control the relative phase of all the signals being generated at a given moment in time. Because it's an IWT, you can also generate multiple frequencies. At the same time, you can also create all kind of complex situations like frequency hopping radars or radar signals where the intermodulation pulse change from one pulse to the next. There is no limitations at all. Okay, let's go for the demo. Basically, the demo is going to consist in those steps here. We're going to calculate the baseband signal for a single isolated pulse. And then this is the signal that we're going to download to the instrument. We don't need to download anything else because we can use the internal timer in the generator to produce the pulses at a given phase. So we can change the PRI by changing this internal generator without having to redesign anything in the waveform. After that, we are going to supply this to the IQ modulator in real time. So we are going to up-sample the signal using the internal interpolator, and we are going to do the IQ modulation, which is necessary because this is an LFM chirp, linear frequency modulation kind of radar signal, so we need to control the INQ components of the modulation. As a numerical modulator, you don't have any problems with aligning the modulator itself because it's by definition perfectly aligned. No distortions, no impairments. Finally, we will acquire the signal, the echo signal, and this signal will be acquired at a sampling rate of 2.4 gigahertz. This means that we are going to use the third Nyquist band of the digitizer, and then we will generate an IF of 800 megahertz. Okay, after that, we will down convert the signal to IQ baseband, we will reduce the sampling rate, and finally we will process this signal to compress the pulses using a match filter that is required for this kind of situation. Okay, so let's go to the Matlab script, and we will just go to the script. I set up different breakpoints, so we will stop at some interesting moments, and then we will take a look at the signal. Okay, so let's launch this. We will connect to the instrument, and then the first thing we're going to do is basically take a look to the baseband signal. So this is the baseband signal for the isolated pulse. This is a 10 microseconds, 5 megahertz LFM signal. That is, you can see the I and the Q components. The I component is the blue wafer, and the Q component is the red wafer. These are the signals that is going to be downloaded to the instrument. The only signal that is going to be downloaded, and it can be, it could be generated at very slow sampling rate, like let's say 400 megasamples per second. So you don't have to generate that many samples. Okay, so once we have generated this signal, we're going to download it. Okay, so basically now the signal has been downloaded to the instrument, and then what we're going to do is take a look to the signal in a scope I have here. In order to have a good vision, I will select the input in the big display, and here we can see the signal as it's being generated. Here you see the pulses, a bunch of them, and then here you can see the spectrum. As you can see, it's a linear FM spectrum, 5 megahertz bandwidth, and at the same time you can see that it's centered at 3.2 gigahertz, as we expected to have. So this is it. After that, what we're going to do is to take a look to the intra-pulse modulation. In order to do that, I am going to select a different setup. It's going to be a radar set 2. Okay, so this is an isolated pulse, and at the bottom you have an automatic analysis of the instantaneous frequency of the pulse. As you can see, as we expected, this is a linear RAM of frequency centered at 3.2 gigahertz, and here you have the duration, which is around 10 microseconds, and the amplitude of the strip, which is 5 megahertz. So this is basically a demonstration of the signal that is being generated. So let's go back to the script. And then the next thing we are going to do is acquire the signal with the digitizer. So we are going to acquire the 3.2 gigahertz signal with the digitizer working at 2.4. Okay, what we are going to see now is the spectrum of the signal. So this is the same spectrum we have seen before in the scope, and I am just showing you the FFT of the acquired signal. As you can see, it's exactly the same thing. But there's a big difference that now, as you see, the frequency is 800 megahertz. This is the central frequency. This is the first step of down conversions, and we have generated an AF signal at 8 megahertz. So the next thing we're going to do is converting the signal to down convert the signal to baseband and do the analysis. So this is the processed signal. So we have taken all these pulses and we have gone through a match filter, and this is the result of the output of the filter. And here you can see, for instance, one of the pulses. We can just zoom on one of the pulses, and you can see the compressed pulse as it was processed by the script. It's important to understand that I use Matlab just because it's nice to show the intermediate steps, but all these processing chain could be implemented in the internal FPGA. So at the end, you could get from the from the Proteus unit exactly this signal, or even a list of parametric description of the radar pulse itself. Okay, so this has been the demo where you can see these important capabilities we have for RF and microwave signal generation and acquisition applied to radar signals. Thanks for attending this small demo, for viewing this video. And then if you have any further question, or you have here my email address, so you can drop me an email in case you have some questions or you need some clarification. Thank you very much.